Here's another example of trying to find the integral of a rational function. We'll use the method of partial fraction decomposition to break up this integrand, this function, into a sum of functions that are easier to integrate. Let's find the integral from 1 to 2 of the function 3x minus 2 on top divided by x cubed minus 8x squared plus 16x on the bottom times dx. First thing to note, this is a definite integral this time. The last few problems that we've done have been indefinite integrals, but as we know, that doesn't matter very much because our process is mostly about finding the antiderivative of the function, which is an indefinite integral. So we'll just do that first, and then at the very end of that process, we will then plug our bounds in and subtract to get the final numerical solution to this definite integral. So I want you to get some practice at doing both definite and indefinite integrals using all these techniques. But really, you don't need to worry too much about the bounds until the very end. So as usual, we'll want to start by noting, first of all, that we have our function is a proper rational function. The degree on the top is less than the degree on the bottom. The degree on the top is 1. The degree of the bottom is 3. So that means that we don't need to do long division first. If you had a higher degree on the top and the bottom, or the same degree on the top and bottom, you would do long division first to sort of split off a polynomial part plus a proper rational function. But here, we don't need to do that. So let's pull our function out of the context of an integral and see what we can do with it. Remember, we want to be able to break this down into a sum of easier functions that are easier to integrate. Our first step in this is always going to be to try and factor the denominator. Now, in this case, our numerator has degree 1, so you can't factor it. It's already factored as much as it can be. But even if the numerator had a higher degree and could be factored, this is a situation where it would not be useful to factor the numerator. But our denominator, we do want to factor. And if we factor this, we can factor out an x, and what we'll find is that if we factor the whole thing, we'll get x times x minus 4 squared. Or you could write that as x times x minus 4 times x minus 4. Same thing. Now, if you think about this, if we try to apply the same breakdown that we applied in our last example, we'll get this. We'll know that we're going to end up writing this as a sum of 3 rational functions here because we have 3 factors for our denominator. We're going to have something over x plus something over the next factor, which is x minus 4, plus something over the next factor, which is x minus 4. Let's put some numbers here. Let's call this a, b, and c. But if you think about it, there's a bit of a problem with our right-hand side expression here. We have 2 different variables, both being divided by x minus 4. Well, those variables b and c aren't going to be unique because you could have, if b turns out to be 3 and c turns out to be 2, you could also just easily have 5 for b and 0 for c. Those two, because they have the same denominator, means you could add them together and just have one number over x minus 4. And it turns out that our theorem that tells us that these rational functions can be broken down doesn't work unless we make a small modification to this. Because the x minus 4 factor in the bottom has a power of 2 on it, we'll actually have to have 2 different rational functions that use it in different ways. The first one will have b over x minus 4, like I wrote. But the next one is going to be c over x minus 4 squared. And this, as it turns out, will give us exactly what we need. This will give us a unique choice of a, b, and c that are all numbers that allow us to break down this rational function. So let's do this. We've got 3x minus 2 over x times x minus 4 squared. That equals a over x plus b over x minus 4 plus c over x minus 4 quantity squared. And the first thing we'll want to do at this point, in order to help us remember, we're solving for a, b, and c. We are not trying to solve for x here. But this, in fact, should be true for all possible values of x. The first thing we want to do is clear the fractions here. So let's actually multiply both the left and right sides of the equation by x times x minus 4 squared. Left and right. X times x minus 4 squared. So on the left, this cancels with our denominator. We have 3x minus 2. And on the right, I'm going to take this expression here that I'm multiplying by and multiply it in to each of the 3 terms in my sum here. Each of these 3 fractions. So if I take a over x and multiply it by x times x minus 4, those x's are going to cancel out, and I'm left with a times x minus 4 squared. Next, if I take b over x minus 4 times x minus 4 squared, well, the x's will not cancel out. I've got a b, I'm going to have an x. The x minus 4 squared on top will cancel with one of the x minus 4 on the bottom, but you're still left with one copy of x minus 4. And finally, we have c over x minus 4 squared. That gets multiplied by x times x minus 4 squared. The x minus 4 squareds get canceled, and we're left with c times x. So now we have a version of this equation that's entirely in a polynomial form. And again, we have to remember, we are not trying to solve for x here. We are trying to solve for a, b, and c. And the key factor that allows us to solve for all 3 of these variables with only one equation is that this equation is true for every possible value of x. That means that we can plug in any numbers we want for x, and every time we do that, we'll get a different equation, and we should be able to solve those equations for a, b, and c. So let's try that. So let's choose a value of x that is convenient for us, that we can plug in for x, and hopefully that will help us to solve for either a, b, or c. In particular, I think I'd like to choose a value of x that causes some of these other variables, the a's and b's and things, to vanish from the equation. And I see that a is being multiplied by x minus 4, and b is also being multiplied by x minus 4. So if I can make those parts go to 0, then I can actually have an equation that only has a c in it. So let's let x equal 4. And let's plug that in. On the left, we have 3x minus 2. That is 3 times 4 minus 2. That equals a, which is unknown, times 4 minus 4 squared, plus b times 4 times 4 minus 4, plus c times 4. Now the 4 minus 4 goes to 0. 4 minus 4 here goes to 0. So we have 3 times 4 minus 2, that's 10. And that equals 0 times a, so I may as well not bother to write it. Plus 0 times b, I won't write that either, plus c times 4, so 4c. That means that c is equal to 10/4, or 5 over 2. So we've now solved for c. So we've solved for c. Let's go down here and let's now make a different choice for x, and hopefully we'll be able to solve for a different variable. In fact, I see that both b and c are being multiplied by x. So if I can make the x go to 0, then I should be able to isolate the a instead. So let's do that. Let's try x equals 0. So 3 times 0 minus 2, I'll just write that in here, minus 2, equals a times 0 minus 4 squared, plus b times 0 minus 4, plus c times 0. So b times 0 times anything that goes to 0, c times 0 goes to 0. And we are left with negative 2 equals a times negative 4 squared, which is 16. So that means that our a is equal to negative 2 over 16, or negative 1/8. Again, as with the last example that we did, we often get fractions for these coefficients. That's okay. That'll happen a lot of the time. You might even find yourself getting irrational numbers. Maybe you're lucky and you get integers, but the only real difference between fractions and integers in these problems is that integers are easier for you to work with. But algebraically, they're just the same. And of course, in calculus, it doesn't matter if you have a number that's a whole number, a fraction, an irrational number. It doesn't matter. They all work the same with calculus. We have one more unknown coefficient to solve for. We know what C is and what A is. We want to solve for B. Here's the problem. We already chose to let x equal 4, which allowed us to solve for C by getting rid of the B and A. We also tried letting x equal 0, which allowed us to solve for A. But those are the only two x values that will cause some of these multipliers to go to 0. If we want to solve for a remaining variable, we're going to have to pick a different number for x. But don't forget, this equation is true for every possible value of x. So if you want to, you could let x equal pi. It wouldn't be very convenient to do that. Let's pick an easy number. But you should be able to pick any number you want for x, and theoretically, that should give you the same result for b, no matter what x you choose. Let's try x equals 1, just for convenience here. So we'll have 3 times 1 minus 2 equals a times 1 minus 4 squared plus b times 1 minus 4 plus c times 1. So 3 times 1 minus 2, that's 3 minus 2 is 1. And that is a times, let's see, 1 minus 4 is negative 3, and if you square that, you get 9. Plus b times 1 minus 4, that's actually going to be minus 3b, and plus 1c, so just 1. How can I solve for my missing variable here? I want to solve for b. Well, I actually already know what a and c are. That's very convenient. Let's fill them in. 1 equals 9 times a, which is negative 1/8, minus 3b, which I don't know, plus c, which is 5/2. So I can rewrite 9 times negative 1/8, that is negative 9/8. And we'll just keep solving for b, right? So negative 3b is going to equal 1 plus 9/8 minus 5/2, except that I can rewrite 5/2 as 20/8 and the 1 as 8/8. This is just arithmetic. You don't need my help for this. And what do we end up with? Well, 17/8 minus 20/8 is negative 3/8. So if negative 3b is negative 3/8, that means that b is positive 1/8. And now we have solved for b. So let's come back to our original rational function, 3x minus 2 over x cubed minus 8x squared plus 16x. We knew that we'd be able to find a choice of a, b, and c, so that this equals a over x plus b over x minus 4 plus c over x minus 4 squared. And we've now found our a, b, and c. So this whole thing equals, let's see, a is negative 1/8 over x plus our b is positive 1/8, that's 1/8 over x minus 4, plus our c is 5/2, so 5/2 over x minus 4 squared. So now we're ready to go. We can fill this back into our original integral and then solve the integral. Let's go back to our original integral and work it out. This equals the integral from 1 to 2 of 1/8 over x. Oops, that's a negative 1/8, isn't it? Plus positive 1/8 over x minus 4 plus 5/2 over x minus 4 squared. And this whole thing is times dx. So we'll just solve the integral. Right? We have negative 1/8 as a coefficient that gets carried along times 1 over x. The antiderivative of that is the natural log of the absolute value of x. Plus 1/8. Well, we have 1 over x minus 4. Again, we can do a u sub for that, but we don't need to actually write it down. We know the antiderivative is going to be the natural log of the absolute value of x minus 4. and we have to divide by the coefficient on the x, but there isn't one, it's just 1, so divide by 1 doesn't change anything. Plus 5 halves. Now, what we have here is an x minus 4 to the negative 2, essentially. So we could do a u sub there, it would be a u to the negative 2. So if we take the antiderivative, we're going to have our u to the negative 1, but we'll also have to divide by the new power, which is negative 1. And the u would be x minus 4. If you need to stop and do the u substitution explicitly, write out what u equals, write out what du equals, do all those things explicitly, you should do that. I'm trying to save some time here because I don't think it's very valuable for you to watch me do those steps. It makes it seem like there are more steps in this process than there really are. And it's good for you to get enough practice at this that you can do a simple u sub like this successfully without having to write it out. But if for now you do need to write it out, then do that. That's fine. Okay, we have our antiderivative here, and we'll just need to write down our bounds, 1 and 2. I would like to clean this up as much as I can before I actually start plugging my bounds in. So this is negative 1/8 natural log of the absolute value of x plus 1/8 natural log of the absolute value of x minus 4 minus 5 halves. And it's actually over x minus 4, so I'll just put the x minus 4 being multiplied by the 2 right there. Going from 1 to 2. So we're ready to go. Let's just fill in our bounds here. Fill in our upper bound. We have negative 1/8 natural log of the absolute value of 2, which is just 2, plus 1/8 natural log of the absolute value of 2 minus 4. 2 minus 4 is negative 2, but the absolute value of that is just 2. Minus 5 over 2 times 2 minus 4, which is negative 2. All of that minus, now let's give ourselves some big brackets here, because we're going to plug 1 into the whole thing, and then subtract that whole expression from the first part. So let's make sure we get it right. We have negative 1/8 natural log of the absolute value of 1, which is just 1, plus 1/8 natural log of the absolute value of 1 minus 4. 1 minus 4 is negative 3, so the absolute value of that is positive 3. This is important, by the way. We're having a lot of natural logs of the absolute value of a negative number. It's important that you don't forget that absolute value because the natural log of a negative is undefined. But the natural log of a positive number is defined. That absolute value is allowing you to actually get a result here. Okay, and minus 5 over 2 times 1 minus 4, which is negative 3. And let's give ourselves a little bit more room here. And let's just simplify our answer, work the rest of this out as best we can, and see what our result is. So I've got negative 1/8 natural log of 2 plus 1/8 natural log of 2. Those two cancel each other out. They're gone. Minus 5 over 2 times negative 2. Well, that means that whole thing is positive, and it's 5/4. Now, let's look at the next part here. The natural log of 1, what power can I put on e to get 1? That's what the natural log function is asking. What power do I put on e to get 1? Well, the answer is 0. So that whole first term there in that brackets is gone. It's 0. Plus 1/8 natural log of 3, but there's a minus sign in front of it, so it's actually minus 1/8 of the natural log of 3. That can't be simplified any further. The natural log of 3 is some number, right? What power do I put on e to get 3? Well, e is a tiny bit less than 3, so the answer is a tiny power a little bigger than 1. But the exact value is just natural log of 3, or 1/8 of that. Okay, minus, well actually, how many negative signs do we have here? We've got 5 over 2 times negative 3. That's 5 over negative 6. But there's a minus sign in front of it, which makes it positive. But there's a minus sign in front of the brackets, which makes it negative again. So negative 5/6. And then we'll just clean up our fractions a little bit here. This is going to be 15/12 minus 10/12 minus 1/8 natural log of 3. So our final answer is we're going to have 5/12 minus 1/8 of the natural log of 3. That is our answer.